Hello. In power electronics, we often come across the term ideal switch. So what is this ideal switch? What are its characteristics, properties? How does it differ from a practical switch? And importantly, why do we care about this ideal switch? Why do we try to understand power converter circuits operation using ideal switches? So these are the things that we are going to cover in this video. So let's get started. First, let's look at a simple switch and its control. This shows a power MOSFET. The main current flows between drain and source. So the drain and source, that is the switch part. G is the gate, that is the control part. Using the gate voltage, you can control the switch operation. So when the drain to source voltage VDS becomes very low, the switch is on. When the current ID is made very low, then the switch is off. When the switch is off, the voltage VDS will depend on the external circuit. When the switch is on, the voltage will be very low, but in a practical switch, it will not be zero. So we control the switch using a gate to source voltage. An auxiliary circuit will be used to generate those gate pulses. And typically, when you give a gate voltage, that switch will conduct. And when you remove the gate voltage or make the gate voltage zero, the switch will switch off. The power MOSFET has a certain characteristics. The switch is operated in certain regions in order to make it behave as a switch. Now this is an ideal switch. So Vs is the voltage across the switch. When the switch is off, of course the Vs voltage will be determined by the rest of the circuit. And when the switch is on, current Is will flow, again dependent on the external circuit. And when the switch is on, the voltage Vs will be zero. When the switch is off, the current Is will be zero. And in order to switch on and off, you need a control. If it's a mechanical switch, you can switch it on or off with your finger. That's the control. Control here is shown by C. By giving some signal here, C, you can turn on the switch or turn off the switch. So a typical switch has three terminals. 1 and 2 is the main part of the switch. So the current flows between 1 and 2, or the current does not flow between 1 and 2, and the voltage is developed across 1 and 2. The terminal 3 is used to control the switch. In power electronics, typically we would like to use ideal switch and analyze the circuit rather than analyzing with the actual power MOSFET or actual IGBT, which is another power device, IGBT characteristics, and so on. Why is that? That's what we are going to see first. After that, we will see what is an ideal switch and the difference between the ideal switch and the practical switch. So why do we analyze power electronic converters with ideal switches? Consider a buck converter. Many of us will be aware of this circuit. Even if you have not done this yet, it is okay. So you have a power MOSFET switch and a power diode. Power MOSFET is a nonlinear active device and diode is a nonlinear passive device. To analyze this circuit together with the power MOSFET and together with the diode, their DC characteristics, their dynamic characteristics, that is difficult. So in most cases, we simplify by replacing the power MOSFET with an ideal switch. Once you replace it with an ideal switch, you notice that when the switch is on, the diode is off, and you get this circuit. Relatively simple circuit to analyze. And when you open the switch, the inductor current flows through the diode. And if you assume that the diode is ideal, then it can be just treated as a short circuit, in which case you will get this circuit, which is again a simple linear circuit, an LRC circuit. The diode also can be treated as an ideal switch. When it is on, it is practically a short. We can ignore the voltage drop across the diode. And when it is off, the leakage current can be neglected and we can take it as an ideal switch turning on and off. The only difference is the diode is an uncontrolled switch. So the more complex buck converter devolves into two simpler circuits. The buck converter simply toggles between these two circuits. So one of the reasons why we use ideal switch in analyzing power converter circuits is, of course, to simplify the analysis. As engineers, we are always looking for simpler models that will do an adequate job. So for model simplification, that is definitely one reason. Even more fundamentally, the power converter circuits are invented circuits, and they have been invented with switches in mind, switches meaning ideal switches. So whoever has come up with this buck converter circuit has invented it with an ideal switch in mind. A practical switch is good enough in many ways, but the basic idea of power converter circuits will emerge only if you replace the practical switch with an ideal switch. That is something to remember. Essential operation of a power converter emerges only with ideal switches. Only when we replace the practical switch with an ideal switch will the operation of the circuit become clearer. Once we have an understanding of the circuit and analysis of the circuit with ideal switches, including ideal diodes, we can then look into the effects of on resistance, for example. What does the on resistance of the MOSFET do to the circuit performance? What does it do to its efficiency? What does it do to the output voltage? How much does it go down because of the on resistance? How does the switching of the MOSFET influence the performance of the circuit? These things are typically treated as secondary effects. The circuit basic analysis is invariably done with ideal switches, including ideal diodes, and then the secondary effects, such as the on voltage drop of the device, the turn on and turn on transients introduced by the device, these are then treated separately as secondary effects. Next, we will see how an ideal switch switches and how a practical switch switches. We will use a simple circuit with a resistance in series with a switch fed by a DC voltage source V in. Generally, when we have a circuit like this, we need not show the V in source separately. We can mark the V in like this. With an inductance, the switching becomes a bit more complicated. We will see that in a separate video. So we will use a simple circuit with a resistive load. First, let us assume that the switch is ideal. In order to control the switch, we need a control circuit which turns the switch on and off, let's say at a particular frequency, with a particular on time and a particular off time. This is T on, this is T off, and T on plus T off is of course T, and 1 over T is the frequency. During the interval T on, the switch is on, so the switch voltage is 0. It's an ideal switch. When the switch is off during the T off interval, Is is 0. So the voltage drop across the resistance will be 0. So the voltage drop across the switch Vs will be equal to Vin. So the switch voltage will vary between 0 and Vin as shown. When the switch voltage is 0, the voltage across the resistance is of course Vin. So the Is current will be Vin by R some value. When the switch is off, Is is of course 0. So we can plot the current waveform as shown. It will toggle between I1, which is Vin by R, and 0 as shown. During the on interval, the current is I1, but the voltage of the switch is 0. So the power loss is 0. So the conduction power loss, that is the power loss in the switch while the switch is conducting, is 0. During the off interval, the voltage is Vin, but the current is 0. So again, the power loss during the off interval, during this interval, is again 0. So because of that, I can plot the power loss curve PS as shown, which is 0 throughout. During the transition with a resistive load, the transition happens instantaneously, so the power loss will be 0. If the load contains an inductor, situation becomes a bit more complicated. We will leave it here. Next, we will see how a practical switch will differ by viewing the waveforms. When the switch is on in this interval, the switch voltage will be very low, but it won't be 0. When the switch is off, most of the switches leakage current will be practically 0. That means the switch is more or less ideally off. So we need not worry about it. And the voltage will be Vin as we saw in the ideal case. So the voltage waveform will be as shown. When the switch is on, the voltage is low but not 0, V on. And when the switch is off, since the current is 0, practically 0, the voltage will be again Vin. If you look at the current waveform, when the switch is on, it will be Vin minus V on divided by R. Switch voltage is V on, so Vin minus V on divided by R. And during the off interval, of course, the current is practically 0. So the current waveform has the waveform shown. I have again marked it as I1 because I'm taking V on to be pretty small. So Vin minus V on by R will be practically close to Vin by R. So the current switches between I1 and 0. Now look at this interval. The switch changes from off to on. That is the T on interval. Small t indicating it is the switching transition interval. So during the interval T on, the switch goes from off state to on state. In a similar way, during the interval T off, the switch goes from on state to off state as shown here. Notice that the transition in a practical switch does not take place instantaneously, whereas in the ideal switch, we assumed that it takes place instantaneously. The current waveform likewise will change from I1 to 0 when you switch off the switch over a period which is T off interval. Likewise, the current waveform goes from 0 to I1 when the switch is turned on over the period T on. So during the T on interval, that is the switching on interval, that is the transition interval, the current is not 0, the voltage is not 0, so the product will give a loss which is the switching loss, the component due to the turning on of the switch. Likewise, during the T-off interval, when you switch off the switch, again, for that short interval T-off, the current is not zero, the voltage is not zero, so the product is not going to be zero. Again, there is a power loss when you turn off the switch. So in a practical switch, there is a turn off power loss, there is a turn on power loss. Put together, they are called as switching power loss. So we can plot the power loss waveform, that is the power in the switch waveform, PS. Again, if you notice this part, this is the conduction power loss when the current flows and the voltage drop is small but not zero. During the off interval, power loss is zero because practically the switch leakage current will be typically be very close to zero. And during the turn on interval, that is the switching transition interval, we should find a better word, switching transition interval, when you turn the switch on, both current and voltages are present, so there will be a power loss that is indicated by this parabola. If you take these two waveforms and multiply them together, you will get a parabolic shape. You can work it out, or we will do it in another video. So this parabola indicates the turn on power loss. This parabola likewise indicates the turn off power loss. So those are marked here. This is marked peak conduction power loss. This is switch off power loss. This is switch on power loss. The switch off power loss and switch on power loss, when they are averaged over cycle and then added together, that will be the total switching loss. Likewise, the conduction loss, when they are averaged over the cycle, then that will be the average conduction loss of the switch. So you have three losses you can identify: peak conduction power loss during turn on, that is the transition, power loss during turn off, power loss during turn on and turn off put together will contribute to the switching power loss. So you can see that the switching action of a practical switch and an ideal switch are going to be different. And the consequences for the power converter operation are also going to be different. Next, we will see what are the characteristics of an ideal switch vis-a-vis the practical switch. At this point, you can pause the video, take a piece of paper and write down whatever you think are the differences between the practical switch and an ideal switch. During the switch off interval, an ideal switch is capable of blocking any amount of voltage. When the switch is off, the voltage Vs will be equal to Vin. That means the switch must be able to withstand that voltage. If Vin is 100 volts, the switch must be able to withstand that voltage 100 volts without breaking down. An ideal switch, of course, is an ideal switch. Even if you apply 10,000 volts, 100,000 volts, it's not going to break down. So it blocks high voltage without any limit. Practical switch, of course, have voltage limits. And also, when the switch is off, in an ideal switch, there is no leakage current. In this respect, most switches are close to ideal. The leakage current will be pretty low. So much so that we don't have to worry about it. Then let's consider the switch on interval. During the switch on interval, a current flows. When the switch is on, the current Is flows, V in by R. In an ideal switch, it can conduct any amount of current. The current can be 1 ampere, 10 ampere, 100 ampere, 1000 ampere, 10,000 amperes. There is no limit. It's an ideal switch. Practical switches have current limitations. So a switch is designed for a particular current and you should not exceed that current. It will heat up the device and it will damage the device. Also, when the switch is conducting, the voltage drop, as we saw across the switch, in an ideal switch is zero, is taken to be zero. In a practical switch, the voltage will be very small, 2 volts, 1 volt, but never zero. Next, the switch transition. An ideal switch is assumed to do the transition in zero time. An ideal switch goes from off to on and on to off instantaneously. A practical switch will take finite time. It will depend on the operating conditions and the switch type, the design, everything. Next, the control. In an ideal switch, you require zero control power. Control power is not an issue to operate the switch. Whether you are switching on the device or switching off the device, the switch does not take any power. In a practical switch, of course, there will be some power expended in controlling the switch. It can become an issue, for example, if your switching frequency is very high, that means you are switching on and off several times a second. Let's say 1 megahertz, 2 megahertz, then the control power, every time you switch on or switch off, if there is a loss of power, the control power can add up. Switching frequency. As you can imagine, an ideal switch, you can switch at any frequency, 1 hertz, 1 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, 100 megahertz, no problem. So there's no limitation on the switching frequency due to the switch, but the technology of the switch, the design of the switch, and the circuit will determine the limits on the switching frequency of a practical switch. Next, we will see something known as quadrants of operation. So I'll briefly tell you what it is. In this circuit, we have assumed that Vin is a DC voltage. So when the switch is on, the switch voltage is 0. When it is off, Vs will be Vin, which is a DC voltage and a positive voltage. So the voltage across the switch always stays positive. Minimum it goes down to is 0. Likewise, the current Is will be 0 when the switch is off. Otherwise, a positive current will flow. The current never becomes negative. The voltage never becomes negative. We can show this on the Vs-Is plane. Here, the switch voltage will always be positive and the switch current will always be positive for this circuit under this operation. So we say that the switch is operating in one quadrant. So the switch operation is a single quadrant operation. Many power semiconductor switches are single quadrant switches. That means they can block voltage in one polarity and carry current in one direction. There are practical switches which can operate in two quadrants. Here is an N-channel power MOSFET, and in the structure of the power MOSFET itself, there is a built-in diode. This diode is part of the structure of the MOSFET, and this diode carries current in the opposite direction to the regular current Is. Here, current can flow in the device both in positive direction, that is in the direction shown, and in the opposite direction. The voltage can be blocked only in one direction. If you apply a reverse voltage, the diode will conduct. We are neglecting the small diode voltage drop. So for this switch, Vs can only be in one polarity, but the current can go in either direction. So in the Vs-Is plane, we can show it like this. Vs is only one polarity, whereas the current can go in both directions. This is a two-quadrant switch. A typical practical switch will be capable of operating either in one quadrant or in two quadrants. Having said that, there are exceptions. For example, triac is a switch, TRIAC, which can operate in all the four quadrants, but that is more of an exception. Most of the practical switches can operate either in one quadrant or in two quadrants, like the power MOSFET with the anti-parallel diode. Suppose I replace the DC voltage with an AC voltage. Imagine, like in your house supply. And this switch can be the switch in your house. Now IS will be an AC current. Of course, V in is an AC voltage, IS is an AC current. That means the switch current direction will be both positive and negative. Likewise, when the switch is off, the voltage Vs is V in, but then V in is AC, so it can be positive and negative. So the mechanical switch that you use in your house can block voltage in both polarities and conduct current in both directions. Such a switch is said to be a switch capable of four quadrant operation. So an ideal switch in general, if you idealize it, an ideal switch will be capable of operating in four quadrants also. That means it can block voltage in both polarities and conduct current in both directions. With this, we have come to this end of this video. In this video, we saw what ideal switch is and why do power electronic engineers analyze circuits using ideal switch. One is, of course, model simplification. Another is power electronic circuits make sense only if you use an ideal switch. We also saw what is the difference between how an ideal switch switches and a practical switch switches. Using a simple resistive load, we did not go into the case with inductive load. It's a bit more complicated. Lastly, we also saw the differences between ideal switch and a practical switch. What are the properties that you will expect from an ideal switch? We have come to the end of this video. If you find this series of videos useful to you and interesting, please consider subscribing and also clicking the like button. Thank you.